Hello, class. Good evening, everyone.
Good evening.
Thank you. Hello, Leah. Thank you, guys. So today we are going to start chapter 4. Okay, today we are going to start chapter 4. Based on the syllabus, we are going to cover the first section of chapter 4, learning some basics about the probability. So we are going to learn two definitions for probability because we have more than one types of probabilities. Yeah, hi, Kayla. So the first definition is the classical definition for probability, and the second definition is the empirical definition for probability. The two definitions are different, so the formulas we use to compute the classical probability is different from the formula we use to compute the empirical probability. Then which formula we use to compute the corresponding probability, then we have to know how to identify which model. We're going to use the classical probability definition formula when the model is classical. And we use the empirical definition when the model is empirical. Okay, so let's start from the definition of a classical probability. Let's see how do we identify if a model is classical. So let's start from procedure. Procedure is a process that gives us some results. Before we apply the procedure, we know all the possible results, but we are not sure which result exactly will occur. For example, toss a coin. Toss a coin is a procedure in probability because before we toss the coin, we assume the surface is smooth, so the coin will not stuck, somewhere. So either we get a head or we get a tail, right? Yeah. Before we toss the coin, we know either we get a head or we get a tail. But exactly will we get a head or get a tail? We are not sure, right? We don't know. Yeah. So that is a procedure. Procedure is a process. Will give us a certain results. Before we apply the process, we know all the possible results, but we do not know which result exactly will occur. So that is a procedure. Another example is roll a die. Yeah, you must have seen what does die look like, right? We are talking about the 6-size die. If you go to casino, you'll see tons of that. Some decoration is the die shape. So the die has 6 sides. It's a cube. It's a cube. It has 6 sides. A fire die. All the 6 sides of the fire die are equal weight. So we have the same chance to get a number 1, number 2, 3, 4, 5, 6. So before we roll the die, we know all the possible results. Yeah, we either get a 1, or get a 2, or get a 3, or get a 4, or get a 5, or get a 6, right? But before we roll the die, we don't know which number exactly will occur. It's very random. So that is a procedure as well. So the first definition, procedure. And every procedure has its corresponding sample space. The sample space is a set. The set contains all the possible outcome, C-O-M-E, of the procedure. Okay, yeah, actually I should switch the order probably. Yeah, we explain what is outcome first. Outcome is a result of the procedure, and the result cannot be further broken down. Yeah, let me write it down. Outcome refers to a result of a procedure. And it cannot be broken down further. Once I give you examples, you would right away understand what does it mean. Okay, so we use capital letter A. Let's say we use capital. Let's say consider rolling a die. Okay, consider rolling a die. If we let A, yeah, we use the capital letter A, B, C, D to represent the results of the procedure. If we let A represents the result that we get a number 6, and then we use B to represent the result that we get an even number. And let's use the definition of outcome to determine which one, yeah, between A and B, which one is an outcome, which one is not an outcome. They are both results of the procedure, right? If you roll a die and you observe the number, yeah, and if the result is number 6, then A occurs. Is A an outcome? Yeah, the definition says a result of a procedure that cannot be broken down even further. Are we able to break the result number 6 even further? Yeah, perfect. A is an outcome. Yeah, cannot be broken down even further. Yeah, to compare with that, we have a B. B is not outcome. Do you agree? Yeah, B is not an outcome. You know why? Because the result getting even number can be broken down into 2 or 4 or 6, right? Do you agree? Yeah, B could be broken down even further. So result B is not an outcome. Result A is an outcome. Yeah, please let me know if I'm clear about the difference between A and B. Why A is outcome, B is not. Perfect. Yeah, if not, you can just let me know, okay? Yeah. Well, then what is B though? B is an event. Okay, what is event? Event is a result of a procedure. When we talk about event, we don't just, we would have to have the procedure as the background, right? Yeah, when we talk about getting even number, we need to have the background over there to make the result eligible, like makes sense, yeah. So you roll a die, let's say you roll a die, and the result is an even number. That is an event. B is an event. A is also event, but specifically speaking, A is an outcome. A is an outcome. All right. Okay. Then now let's go back to sample space. Every procedure has a sample space. Sample space is a set that containing all the outcomes of the procedure. Yeah, let me write it down. Sample space refers to a set, is a set containing all the possible outcomes of procedure. When we talk about sample space, it must be a certain procedure's sample space. It's not just a sample space. So those are two things always go together. Yeah, this, let's say S is sample space. Then the sample space of what? Of a certain procedure, right? Yeah, can you help me to find a sample space for the two procedures that I had here? Yeah, this one is toss a coin. We use a capital letter S to represent the sample space. This is the set notation. Okay, yeah, let's see what is the sample space of the procedure that toss a coin, and what is the sample space of the procedure that we roll a die. It's a set containing all the possible outcomes. So if we toss a coin, what are all the possible outcomes? And those outcomes cannot be broken down even further, right? Heads and tail, perfect, exactly. So we would normally use H to represent the head, use the capital letter T to represent the tail, and that's it. Okay, that's it. So what about the sample space of rolling a die? When we roll a die, what are all the possible outcomes of that procedure? Yeah, 1, 2, 6, perfect. Yeah, so we want to write them out. 1, 2, 3, 4, 5, 6. Exactly. All right, perfect. Yeah, with those basic concepts covered, now we can talk about what is a classical probability model. Okay, yeah, a classical probability model. Probability model is a procedure that satisfies the following two conditions. Let me write the two conditions. Which two conditions? Number 1, the sample space is finite. In other words, the sample space contains a finite number of outcomes. Yeah, S contains finite number of outcomes, not infinitely many, finite number. Yeah, so earlier, toss a coin, we have 2 outcomes, right? So 2 is a finite number. And rolling a die, sample space has 6 outcomes. 1, 2, 3, 4, 5, 6. Yeah, 6 is finite. So if a sample space has a million outcomes, a large number of outcomes, but as long as it is finite, as long as it's not infinite, it satisfies the first condition. Okay, yeah, sample space is finite. Yeah, means the sample space only contains finite number of outcomes. The second condition is all the outcomes are equally likely. Equally likely to occur. OCCO. You are. Yeah, all the outcomes in the sample space, they have the same chance to occur in the procedure. All right, if both of the two conditions are met, then we are looking at a classical model. Yeah, let me know when you finish the copy. It's pretty straightforward to determine if a procedure, a classical model. Think about toss a coin. We have two outcomes, right? Yeah, we assume the coin is fire, so we are not cheating. It's not one side is heavier than the other side. If the coin is fire, then we should have 50% chance to get a head and another 50 chance to get a tail, right? So that means the two outcomes are equally likely. Both conditions are met. So toss a coin is a classical model. I would say the most basic classical model. If we look at rolling a die, the procedure of rolling a die, and the sample space has 6 outcomes, finite number, and all the 6 outcomes also equally likely to occur, right? Yeah, we have a 1/6, that many chance to get the number 1. We have a 1/6, that many chance to get the number 2, and so on and so on. We have a 1/6, that many chance to get the number 6, right? Yeah, as long as the die is a fire, we all normally just assume it's a fire. If we're not specifically pointed out, it's not. Any question about the definition of a classical model? Any question about the definition of a classical model? I think I made it very clear. Yeah, you just need to find a sample space, right? And look at all the outcomes to see if we have a finite number of outcomes, and also are they equally likely to occur, right? If both of the two conditions are met, then we are looking at a classical model. Okay, so if we have a classical model, this is the formula for us to compute the classical probability. So when we talk about probability, we don't just say probability equals what? We have to say probability of what? Probability of an event, all right? So this is an event. Yeah, we use a capital letter A, B, C, D, those to represent events. Remember, event is a result of the procedure, and the P here is the probability. So this notation is the probability of event A. And if we write the words that describe the notation, yeah, it is the probability OF of event A. Okay, yeah, the probability of event A. Yeah, let's say we are looking at a classical model. Then in a classical model, we use this formula to find the value of P of A, yeah, probability of A, the chance of A occurring, or likelihood of A occurring. Yeah, what's the formula? The formula is K over N. Okay, yeah, it's a fraction. It's a fraction. Let me explain what's the denominator, what's the numerator. The denominator is the number of all the outcomes. Yeah, in other words, n is the sample space size. Yeah, how many outcomes in the sample space? When we toss a coin, we have 2 different outcomes in the sample space, so n is 2. Yeah, when we roll a die, we have 6 different outcomes. So 6 is the value of n. Yeah, let me see if it's clear. So n is a number. Yeah, n is the number of all the outcomes, or n is the total number of outcomes. N is the total number. Total number of all the outcomes in the sample space. In a sample space. Yeah, what is sample space? Sample space is the set that containing all the outcomes. Outcome is a result that cannot be broken down even further. So that's the denominator. And what about the numerator? Numerator is the number of outcomes in a sample space that favor event A occurring. Okay, once I give you an example, you would understand right away. Earlier, we were talking about rolling a die, right? Yeah, let's do rolling a die again. And remember, A represents getting number 6, right? And B represents getting an even number. Yeah, do we remember what is even number mean? Even number are integers. Even number refers to an integer that is divisible by 2. It has a factor 2. Yeah, it has a factor 2. Ooh, where's my note? Yeah, let me double check. I'm recording. I'm sharing. I think my my notes just automatically close it yourself. Okay, we're here. Yeah, so rolling a die has sample space containing 6 outcomes. Right? Yeah, do we agree rolling a die is a classical model? It is classical. Yeah, why is it classical? Because sample space has a finite number of outcomes. And all the finite number of outcomes, the 6 outcomes are equally likely to occur because it's a fire die. Yeah. Then in this model, we are going to use the formula here to compute the probability. Yeah, let's see how do we get at that. P of A, P of B, P of A. The denominator is the total number. The denominator is the number of the total number of the outcomes in the sample space, or the sample space size, right? It has 6 outcomes, so 6. Same thing here, right? Yeah, because they belong to the same procedure. Yeah, the denominator, both of them are 6. And among the 6 outcomes, how many of them? Yeah, so 1, 2, 3, 4, 5, 6. Among the 6 outcomes, how many of them favor A occurring? A here is we getting number 6. 1, exactly. If we get a number 1, then A doesn't favor A, right? We get a number 2, doesn't favor A. Get a number 3, doesn't favor A. 4 does not, 5 does not. Only when we get the number 6, we favor A occurring. So the number of outcomes in a sample space that favor A occurring is 1. So the probability is 1, right? Yeah. We probably know it's 1 over 6 already because A is outcome. But use this formula, we get a consistent result. And what about B? Denominator, we know is 6 also. Yeah. And among the 6 outcomes, how many of them favor B occurring? If we get the number 1, I don't think it favor. But if we get a 2, 4, 6, and that favor B occurring, right? Because those are even number. Yeah, exactly. Awesome. 3. So the probability is 3 over 6. Can we reduce 3 over 6? It's a half, right? It is half. Yeah. Sometimes, in order to sometimes if we choose different sample space, and we are able to get a problem done even faster. Yeah. For example, rolling a die. And the even B represent the result that we get an even number. Of course, we use the sample space as 1, 2, 3, 4, 5, 6. We got a probability half, right? But if we consider, we roll a die, and this time we roll a die, we do not record the number that we get. Instead, we record, do we get even or odd? Yeah, we change the recording, we change the way we look at sorry, we change the way we look at the result. Yeah, instead of write down the number, we observe the even or odd of the number. Yeah, so this sample space has two outcomes, right? Two outcomes. Yeah, because our observation is to look at if the result is even or odd. They are outcomes. Depends on what you concern from the result, right? Yeah, we are not recording the number now. We are recording if the number even or odd. Yeah, observation is different. So those are the two outcomes. And are those two outcomes equally likely? They are equally likely because three of them are even, three of them are odd, right? So this is also a classical model. So in this classical model, if we properly choose the sample space, we can make finding the probability sometimes even easier. Then the denominator would be 2 and the numerator would be 1, is 1/2. Okay, I'm just saying sometimes we can be flexible a little bit and make our job even easier. Am I clear about that, guys? Yeah, that's how do we compute. That's how do we apply the formula. Thank you. That's how do we apply the formula to compute classical probability. Classical probability. Let's look at the formula one more time, okay? Yeah. P of A, the notation, represents the probability of event A. Yeah, P is the initial probability. The capital A here refer to an event. Yeah. And then the formula is a quotient or fraction. It has a numerator, it has a denominator. So if we apply this formula, we just need to find the two numbers, one put on the top, one put on the bottom. The bottom one, the denominator, is the total number of outcomes in a sample space. Yeah, once you have the procedure, you need to identify the sample space. You have to do that anyway because you need to determine if the procedure classical or not classical, right? Yeah, in order to do that, you have to look at the sample space. So sample space is very important. And the numerator is related to the event A. Yeah, we're going to look at those outcomes in the sample space to figure out how many of them favor event A occurring. Yeah, something like that. All right, so this is the definition of a classical model. Yeah, how do we know classical? We have to look at the sample space. If it has a finite number of outcomes and all the finite number of outcomes are equally likely to occur, then it's a classical model. Yeah, we use this formula to compute the classical probability. In the classical model, the probability of an event is called the classical probability. All right, if you guys do not have any question about classical model, we're gonna go to look at an empirical model, okay? We're going to look at the empirical model. The second definition is the empirical probability. Definition of empirical probability. Let me close that. Sorry about that. So my personal device probably have some virus. Yeah, empirical probability model. Let me move this a little bit here. Okay. How do we know if a model is empirical? That's easy. You know why is it easy? Hold on. Let me rewrite this. Empirical. Empirical means based on experiences, right? Yeah, probability model. Yeah, and it's easy. Why is it easy? If the model is not classical, it's empirical. If the procedure, okay, yeah, if the procedure is not classical, then it's empirical. That's enough for us. Yeah, we do have a third type of probability, but we don't really cover it. All right, it's subjective probability, but we do not really cover it. So for us, either classical or empirical. If it's not classical, then it's empirical. So let's look at an example. Procedure. Yeah, let's look at a procedure. Let's say our procedure is to survey our class, yeah, our class. Oops. And then we are going to write down. We are gonna ask question: do you smoke cigarette or not? Okay, we concern if the subject, you guys are all subjects, including me. Okay, no, I'm the researcher. I'm going to survey you. So all you guys are the subjects. I'm going to ask you: do you smoke? Do you smoke cigarettes? Yes, smoker or not smoker? Non-smoker. Yes, survey. Do you remember surveys? I ask every single one of you, right? And I record on my paper. I have my data set. Yeah. So we want to find the probability of randomly select a subject and the subject is a smoker. Yeah, let's consider this probability. Okay, guys, we have the procedure explained, right? What is the procedure? I'm going to survey you guys. I'm gonna ask you, are you a smoker? And then write it down, right? Yeah, so that's my procedure. And I'm going to randomly select a subject and ask if you're a smoker or not smoker, and then I'm considered to find the probability of it. So what do you think? What's the sample space in this problem? Yeah, of this procedure. What is the sample space of the procedure? Do we have outcomes in the procedure? What are the outcomes? My procedure is to write down smoker or non-smoker, right? Outcome is a result of procedure, cannot be broken down even further. Actually, since I'm writing down if you are a smoker or not smoker, so my outcomes is smoker and non-smoker. You see I'm talking about non-smoker because I concern non-smoker. My procedure is to randomly pick a person. Actually, let me repeat this. Randomly pick a person. I rewrite this. Randomly pick a student in a class. Yeah, and ask, do you smoke or not smoke, right? Yeah. So, or before I ask you, I don't know. Well, after I ask you, of course I know. So what is the result? Result is either you are a smoker or you are not smoker, right? Do you guys agree? Yeah, either you are a smoker or non-smoker. Outcomes would be, yeah, exactly, perfect. Yeah, exactly. Yeah. So in this procedure, that's our sample space. And the sample space can turn two outcomes. Now my question is, are the two hold on, let me see. Are the two outcomes equally likely? Are the two outcomes equally likely to occur? Would I say like like toss a coin? Would the smoker and the non-smoker 50%, 50%? No, you're right. No, really not. Okay. It also depends on the sample I get. if I randomly pick a person in our class, and the chance of getting smoker would be different from the chance I pick a smoker in my other classes. You see what I'm talking about? Yeah, the chance is different. Definitely not 50%, 50%. So those two outcomes are not equally likely. That means what? It is not classical. It is not classical. If it's not classical, what is it? It is empirical. Okay, it is empirical. Am I, clear about that? It is empirical. Okay. All right. So it is empirical. So in an empirical model, how do we find the probability? In an empirical model, this is the formula to find the probability. F over N. N here is sample size. Yeah, let's not consider population. Let's consider sample size. How many people in our class, right? How many subjects I have? Yeah, sample size. How many of you? Let's see. 16. No, including me, 16. So 15. Yeah, and the F is the number of smokers in the sample. Okay. So the chance, the probability of randomly select a subject from sample and the subject and the subject is smoker actually is the relative frequency. Do you guys remember relative frequency, guys? This actually is a randomly frequency. A relative frequency. Yeah, let's say among you guys, 15 of you, 5 are smoker. Then it's 5 over 15 or 1/3. Yeah. So I have the probability of randomly select a subject and the subject is smoker is 1 over 3. Okay. I think a better way to describe this experiment or procedure is right here. I have this. Yeah, here. Sample, yeah, right here. Sample 10,000 people. Result shows 250 of them are smokers. The empirical probability of randomly select a person and the person is a smoker is 250 over 10,000. Reduce the fraction, we have 1 over 40. So the chance of getting a smoker if we randomly select a subject is 1 over 40. You see the N is the sample size, right? Yeah, sample size. And the numerator is the frequency. Smoker appears 250 times. We have 10,000 trials here. You asked, do you smoke or do you not smoke? So the smoker appears 250. So the smoker has a frequency 250. Use the frequency to divide by the sample size. We have the relative frequency. That actually is the empirical probability. Am I clear about that? So the formula is different, right? Empirical probability. Any question about the definition of empirical model and the formula? Okay, awesome. Thank you. Yeah. So now allow me to spend a little time to explain empirical probability. Okay. Empirical probability, you know what? Is just an estimation. Estimate. Yeah, let me make an analogy. I would like you to understand what is empirical probability, or what is really probability. Probability here means the actual probability, the chance of the event occurring at a certain circumstances. And the probability of a certain event is a property of that event. It's like the color of my eyes, the skin color of me, a person, is part of me, is a property of me. You know, is something objective. You know, it doesn't change because you wanted it to change, right? Unless you dye the hair, but it's not a natural color. I mean, the natural color is my property. It's something objective, not subjective. Okay, the probability of an event is part of it. Yeah, is an objective existence, and the value of the probability measures the chance of the event occurring in one trial of the procedure. And the value of the probability is also objective existence, is a certain value. Yeah, is a certain value. In the classical model, we are lucky enough, we are fortunate enough to find the exact value. So the classical probability is the actual probability of the event. However, in the empirical model, there's no way we can find exact value of the event. There's no way. Yeah. And we can only, yeah, for example, we want to know the probability of randomly pick a person who is a smoker of the United States, yeah, the whole country. It's really hard to find it, you know, it's really, really difficult. What is the probability? It's also very complicated, because at the same time, probably some people they quit it, right? Some more people maybe they started to smoke again. So it's very complicated, and it's not possible for us to find the exact value of the probability. We can only what? We can only estimate. We can only estimate. Let me give you an analogy. Let's say we have a table here. Okay, this is my table. And the length of the table, is an objective existence, right? Yeah, and there's a value there. Yeah, there's a value. How many feet? But how many inches? Yeah, inches make more sense. But I don't know. You know, there's no way I know what's the exact value of the length. But what we can do is what? We can measure. We can only measure. And the measurement I get probably different from the measurement that you get. Even they are very close. Very likely there's a difference, right? Yeah. So same thing. The probability is the actual value of the probability is an objective existence, but we cannot actually find the value. We can only measure. How do we measure? We use the frequency, relative frequency, to measure it. Yeah, similar with measuring the table length. In order to make it as accurate as possible, yeah, get an estimate as close as possible to the actual value, we can measure probably n times, right? Yeah, use different tools, use a different person, because the person has a subjective judgment. Yeah, so we measure many times. Okay, many times. Let's say n times, and then we take the average. And when the n approaches infinity, the average of those, we should know what is the average, right? Mean. Yeah, the average of those measurements would be very close to the actual length, actual value of the length, right? Yeah, same thing for probability. We use the frequency, relative frequency, to measure the probability. And when our sample size is big enough, yeah, very large sample, then the relative frequency, the empirical probability would be very closer to the actual probability. Does what I said make any sense here? It's something I really want to share with you, then you can understand probability better. Instead of just know how to compute it, we want to really understand the concept. Let me know. Yeah, the frequency, the relative frequency here is just the estimation of the actual probability. Because in an empirical model, there's no way we can find the actual value of the probability. We can only estimate. How do we estimate? We use F over N to estimate. And how do we make it as accurate as possible? We want the biggest sample. Yeah, when the sample size is bigger, then the estimate is more accurate. Any questions? Hello? It makes sense. Okay, thank you, Leah. Okay. I hope you paid attention, guys, other students. Okay, very good. Okay, so those are the basic concepts about the probability. Okay, 2 definitions. Now we are ready to do problems. Yeah, I print out the whole section of 4.1. Here is the whole section of 4.1. Let's find some problem. Instead of going to Pearson, like loading for a long time, and you know, I print them out and I paste it on my notes. Let's look at number 6. We do not learn that yet. Let's look at number 1. The what for a procedure consists of all possible simple events or all outcomes. Yeah, outcome have another name. It's called a simple event, just a different name, that cannot be broken down any further. What do you think? 1, 2, 3. Sample space, right? Sample space of a procedure consists all the outcomes that cannot be broken down even further. Okay. Number 2, the classical approach to probability requires that the outcomes are what? In order to be a classical model, the sample space can only have a finite number of outcomes, and all the outcomes are what? 1, 2, 3, equally likely, right? Number 3, as a procedure is repeated again and again, the relative frequency, you see that? When you see that, you know it's empirical, right? Of an event tends to approach the actual probability. This is known as, yeah, we didn't cover that, is the law of large numbers. The law of large numbers. So when you repeat a procedure over and over time, when the n number of trials or sample size is large enough, and the frequency, relative frequency, very close to the actual probability, it is called the law of large numbers. You might or might not heard of it. It's very important law. You only see that one time in the homework. We focus on computing the value. Okay, so events. There are 2 types of special events, by the way. Some event always occur. If the event always occur or certain to occur, then we say that event is certain to occur and the probability is 1. Okay, for example, if we consider rolling a die, if I let C be getting a number 7 and D as the event that get a number less than 7, which one is certain to occur? D, yeah, D is certain to occur. Which one is not possible to occur? C. Yeah, thank you. So those are two special events, two special types of events. Yeah, D is certain to occur. C is not possible to occur. Then do you agree? Probability of C is gonna be 0, and probability of D is gonna be 1. And there are two extremes. Yeah, all other random events, their probability all between 0 and 1. Okay, yeah, all the probability is between 0 and 1. When the probability is 0, that means the corresponding events not possible to occur. When the probability is positive 1, that means the corresponding event always occur, certain to occur. Yeah, probability here is a measurement that measures is a value. Probability is a value that measures the likelihood of an event occurring. Yeah, and the value of the probability always between 0 and 1 inclusive. Yeah, bigger than or equal to 0, less than or equal to 1. In the case the probability equals 0, that means the event not possible to occur. In the case that probability equals 1, that means the probability always occur, certain to occur. So now we should be able to answer this question. Which of the following is not a principle of probability? Yeah, read it and tell me. Is not. A says all events are equally likely in any probability procedure. B says the probability of an event that is certain to occur is 1. C says the probability of any event is between 0 and 1 inclusive. D says the probability of an impossible event is 0. You guys great. Perfect. Not always equally likely, right? Empirical model is not equally likely. Only classical model. Yeah, of course we have other models, but we only talk about two models. Yeah, only classical model is likely, equally likely. Very good, very good. Next. Yeah, we're gonna have a new concept now. Yeah, what is that? What is the P of A bar here? Yeah, what is A bar? Let me show you the definition. A bar represent an event. Okay, yeah, what event? A is not occurring. All right, yeah, for example, if we roll a die, yeah, again, rolling a die. If A is getting an even number, and what is A bar? Sorry, A bar. Get an odd, right? Yeah, not getting even number, then we definitely get an odd. Yeah, exactly. Yeah, just the is not, some people they say opposite, but we don't really use that terminology. The correct terminology is a complement. A bar is the complement of A. Okay, A bar is the complement of A, is the name of A bar. It refers to the result that A is not occurring. So A and A bar have no common outcomes. Yeah, A and A bar have no common outcomes. All right. So now let's talk about an empirical model. Let's use A to represent tomorrow raining. Oops. A is tomorrow. Tomorrow raining. And B, not B, sorry, A bar. And what is A bar though? A bar would be tomorrow not raining, right? Okay, let's say somehow we know probability of A is 20%. Can anybody tell me what is the probability of A bar? Yeah, if we know tomorrow the chance of raining is 20%, what is the probability of A bar? A bar is the complement. Yeah, it's important that we know the name of those notations. Yeah, it's not 80, it's 80%. Yeah, exactly. You know why is 80 has to, the percent is so important? Because remember, probability is a value between 0 and 1. 8 is too big, right? Yeah, it's a percent because 20% convert to decimal 0.2. 80% convert to decimal 0.8. Yeah, if we say 0.8, that's correct. Yeah, technically, if you say 80 is incorrect. Yeah, it has to be 80% or 0.8. Yeah, the probability always a value. Yeah, thank you. Probability is always a value between 0 and 1, including 0, including 1. Yeah. Yeah, why? Yeah, you guys all know that. Yeah, what does that mean? It means this. Means you agree with this formula, okay? Yeah, that's the formula. Yeah, that's the complement event formula. The probability of event A plus the probability of the complement of A always equals 1. The sum of the probabilities of two events, if the two events are complement of each other, always equals 100%, which is 1, okay? 100% is 1. Yeah, remember this example, then you know how to do that. For example, then let's look at this one. Let's look at number 6. If A denotes some event, what does A bar denote? If P of A is 0.996, what's the value of P of A bar? So firstly, what does A bar denote? Yeah, A, B, C, D. Oh, awesome. Very good. How do you get that 0.004? You use 1 to minus it, right? Exactly. Yeah, you use 1 to minus it. Or you subtract 0.996 from 1. Yeah, I would say that's pretty straightforward. And A, B, C, D, which one describe the meaning of A bar, the notation? B, let's see, what is B? B says event A bar denotes the complement of event A, meaning A bar consists of all outcomes in which event A does not occur. Very good, very good. So when it comes to P of A and P of A bar, we have another definition, it's called as. Yeah, we have so many things to cover. Every time I feel like we don't have enough time. Okay, now let me give you another pair of definition, okay? Another pair of definition. Well, that's very big. I was written that so big. Another pair of definition, as favor and as against. So firstly, let me this, yeah. So another pair of definition. Let's say we have an event A and its complement. Yeah. And we define the as favor A. Yeah, we define the as favor A as a ratio. Yeah, ratio of A. Ratio of what? Ratio of P of A and P of A bar. You know, ratio can be written as this as well. Right? Or we can write a ratio as a fraction. Yeah, we have different way, or sometimes we write this 2. Right? Yeah, it has 3 different forms. Yeah, we use this one the most of the time. Use a fraction. The yellow one. I'm coloring orange. Yeah, coloring orange. All right. Yeah. So the other definition, the as against A occurring is a reciprocal. P of A bar on the top, P of A on the bottom. Okay. The important thing I want to explain is as is different from probability. Even is closely related to probability, but is different from probability. Probability is a value, one value. The value has to be bigger than or equal to 0 and less than or equal to 1. But odds, you know what is odds? Odds is a ratio. Odds is a ratio. Okay? Yeah, odds is a ratio. You can write odds as the ratio like in this format, right? For example, I think we'd better give an example. Yeah, let's consider rolling a die. Let A be get the number 6, all right? And what's the odds getting number 6? Yeah, when you go to casino, they probably will not use the word probability at all. Even the whole mathematical branch, probability and statistics, originally come from the gambling industry. But if you really go to the casino, nobody probably use that probability. They would say odds, right? Yeah, what is the odds? Yeah. So let's say what's the odds of A? Yeah, then in order to know the odds of A, we have to find out what is the probability of A and then what is the probability of A bar, right? Anyone can help me with that? What's the probability of rolling a die and getting number 6?
1.
Yeah, let me repeat it. So the procedure is rolling a die, and the A represent we get a number 6. What's the probability? What's the chance? Rolling a die and we get a number 6. Do you mean 1 over 6? Yeah, 1 over 6. Very good. And anyone can tell me what is the probability of A bar? 5 or 6. Awesome. Very good. Yeah, 5 or 6. Very good. They must add up to 1, right? Perfect. Yeah. And now we can, then what's the odds of A? Odds of A is a ratio. Yeah, not a one value. It's a ratio. The ratio is 1 over 6 to 5 or 6. If we simplify that, is 1 to 5. If you go to casino, that's what you that's what you hear most of the time. Yeah, the odds of A, let's say if we get number 6, we win. The odds of winning is 1 to 5. It's very different from probability. Yeah, even we use the probability to figure out what's the odds, but it's not probability. And anybody can tell me what's the odds of losing? What's the odds against A? And this time we go A bar first. Probability of A bar to probability of A. Yeah. So the odds against the winning is 5 to 1, right? Yeah. But normally in our book, you probably want to just write as a fraction. So 1 over 6 over 5 over 6. So that's a 1 over 5. And this one is 5 over 6 over 1 over 6 equals 5 over 1. Yeah, you can just say 5 over 1. Yeah. But in reality, they do this first. 1 to 5 or 5 to 1 is a ratio. Yeah, again, I want to emphasize odds is a ratio, not a one value. Yeah, that's very important. Yeah, after the class, you don't say just odds is the probability. No, odds is not probability. Odds is a ratio. Okay, yeah. And we don't have a lot of problem about odds. I see this one. We can do it. The odds. Which one? Number 5. Yeah, number 5. Number 5. The what in favor? What are the ratio P of A over P of A bar? Yeah, the odds favor A is that ratio. Okay. Yeah, it says actual, but sometimes we don't really have the actual. Actual is not keyword. In favor is the keyword. Okay, favor A is the keyword. Yeah. And we got number 6, number 7. Okay, this is a good question. How do we understand the definition of probability? Yeah. Which of the following cannot be probabilities? Which of them cannot be? Cannot be. So you will have to pay attention. Cannot be. You don't choose the values that could be, right? Is a negation. 1B probability. If the probability is 1, then the event is certain to occur, right? Yeah. Could sorry, I'm going to do here. Yeah. Yes, 1 could be a probability. Could a negative 0.44 be a probability? We never say probability is negative. I don't even know what that means, you know. Probability never be negative. Yeah, exactly. Never be negative. And could a 0.03 a probability? Why? Because it's between 0 and 1, right? Could a 3 over 5 be a probability? Could a 5 over 3 be a probability? Yeah, why not? 5 over 3 is bigger than 1. Not possible, okay? Could a 1.55 be probability? Too big, bigger than 1? No. Could a root 2 be probability? No, because the root 2 is around equal to 1.414. 1.41. Yeah, I don't remember exactly. Yeah, 1.4. Yeah. So anyway, it's bigger than 2, bigger than 1. So no. Could the probability be 0? Yes, right? Because is impossible. If the event is impossible, then the probability is 0. All right, and this is a very good question. Very basic. And we do have to find some problem that actually we compute the value. Let's see, do we have any classical here? Yeah, when we see casino, you know, all the games in casino, classical model. Let's look at number 11. We are looking here, number 11. 11. For a certain casino slot machine, the odds is about the odds. Okay, the odds in favor of winning is 37 to 63. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusive. Okay, so basically, we are considering the result winning, right? Yeah, we know the odds of winning is 37. Yeah, let's use W to represent the winning. W, capital letter W, to represent the winning. That means P of W over P of W bar is 37 over 63. Do you agree that? In favor winning, 37 to 63, right? Yeah. And how do we find the probability though? If we divide both top and bottom by 100, then we would have P of W equals 37 over 100. Yeah, P of W bar equals 63 over 100. And you know what? This way we guarantee P of W plus P of W bar equals 1. Yeah, you might wonder, how do you know divide by 100? Do you always divide by 100? Not always. You have to divide by a number such that the two probability add up to 1. Yeah, in this case, how do I know it's 100? Because the 37 plus 63 happen to be 100. So that's that's how I know. If I divide by 100, I would make the sum of the two probabilities be 1, right? 37 over 100 plus 63 over 100 is 100 over 100 is 1. So that works. So the probability of winning would be 37 over 100, what is 0.37, right? Yeah. Okay. Any questions? A lot of content. To be honest, I really think, how could we learn so much just in one class? So many details I want to cover. And you probably want to watch the video one more time and or just find the important part to watch again. I have a classical model actually to, oh, perfect. Number 13. Number 13 is a classical. Play cards, right? Yeah. Yeah. Now we are looking at number 13. Yeah. Now we are looking at number 13. You are certain to get a number or a face card when selecting cards from a shuffled deck. Express the indicated degree of likelihood at a probability value between 0 and 1 inclusive. This is not a very good question. This is a special case. You are certain, look at the keyword. You are certain to get a number or a face card. Of course, you either get a number cards or you get a face card, right? Yeah, 1 through 10 is number card. J, Q, K, they are face card. Yeah. Then what's the probability that you either get a number card or a face card? If you're certain to get that. If you're certain to get a result, what's the probability of the result? Certain. 1. Perfect. Thank you, Dustin. 100%. There we go. It's 1. Yeah, we don't even have to use a formula, right? And we do need it though. Let's see, do we have any other classical? No, those two are empirical. Let's look at the number 14. Those are good problems though. Number 14. When you see a table, that probably is empirical. Yeah, because it's from an experiment, from the result of a sample or survey, you know. Here, number 14, refer to the sample data for pre-employment drug screening shown below. If one of the subjects is randomly selected, what is the probability that the test result is a false positive? Yeah, this is actually a very interesting problem. Yeah, we have tons of tests, right? And those tests, they are not 100% reliable. Yeah, they are not 100% reliable. There is an error. As long as the error is controlled within a certain range, that test is still a good test. Yeah. So here, that's why we have a false positive, false negative, something like that, right? Yeah. Who would suffer from a false positive result? Why? Yeah. So here, the first part, we are looking for the probability of a false positive result, false positive test result. Yeah, some problem like this, we need to spend time. Yeah, don't rush. Spend time to read the questions through, yeah, thoroughly, and understand the table, especially the table, okay? Especially the table. So the table here, you know, if I were you, I would always do this. Yeah, I would too thick. Extend the table. I'm going to have one more row and one more column. And here's the total. Here's also total. Yeah, because that would make our job later easier. Yeah. So I'm gonna add up the first row, 46 plus 13, that gives me 59. Second row, add up 51. Let me double check. 59. And this one, 15 plus 3, 6, 51. Right? And then by column, 46 plus 15, we have, what is it? 71, right? And 13 plus 36 is 49, right? Do you agree? $49, and this one, ooh, 61. My bad. Oops, 61. This is 61. 4 plus 1 is 5, so 61. And also, what is this? Altogether, what do we have? Altogether, we have 110, right? Yeah. And that is 110 as well. Yeah. So you want, when you do the problem in MATLAB Math, all those problems are MATLAB Math problems. You have to do it anyway. You want to extend the table and find the totals for each row, find the totals for each column, and find the total for all the cells in the table. Okay. Yeah, all the numbers in the table. So now let's look at the table. This table has two variables. Yeah, by row, we have use drug or not use drug, right? Yeah. Can you tell me how many people use drug? Then you understand the table. How many people use drug? Let's see. Yeah, let's at least finish this question, okay, guys? Yeah, exactly. That means you understand the table. Then we have 51 people do not use drug, right? So we have in total 110. 110 is the total number of the subjects here. Among the 110 people, 59 use drugs, 51 do not use drugs. Yeah. And now let's look at the column. Among the 110 people, how many of them are tested positive? And how many of them are tested negative? Let me just ask one. How many of them are tested positive? Among the 110 people, how many of them are tested as a positive? Exactly, thank you. That means you understand the table. And tell me, among the 110 people, how many of them are tested are false positive? False positive. False positive means the person does not use drug, but the result is positive, right? Can you tell me how many of them? Perfect, 15, exactly. And you know what? 15 is the numerator. And what's going to be the denominator? Total number of the subjects or sample size, right? So this is empirical. Yeah, empirical. Awesome, exactly. So you just use 15 to divide by 110. You would have a decimal. What answer to enter? Look at it here. Please always paying attention to the sentence in the parentheses. If they ask you to enter decimal, please do not enter fraction. All right? Yeah, read this part. It says round to 3 decimal places. And you have to do what it asks you to do. Otherwise, you get it wrong. Yeah. So the answer is 0.136. Exactly. Very good. All right. Yeah, there are more problems in this section. Yeah, I would like you to practice. If you ever have any questions, please feel free to email me. All right, I'm here to help you. Yeah. Yeah, perfect timing, 8:50. Let me take a picture. Don't go yet. Let me take a picture of your attendance, and then we can rest for the day. All right, guys. Thank you, guys. I'll see you on Thursday. Bye-bye.